Hi, welcome back. This is Unit 5.3, and this is going to be on nomenclature, and this is naming. Nomenclature means naming. So we're going to dive into how to name ionic and covalent compounds and molecules. Now, this is meant to go along with the notes handout because it's fill in the blank. We're going to fill these notes in as we go. So if you're at home watching this, make sure that you have that printed out. It's the same thing that I have on the screen so that you can fill this out. Also, this is a very, very long video because I go over so many examples, and it's not meant to be done in one sitting. So I want you to do this and break it up into smaller pieces. Or if you want to get it all done at once, you can do that as well. All right, starting off, let's talk about main group elements. And I've mentioned this before, main group elements. So let me pull over my periodic table here. Main group elements are going to be groups 1 and 2. So it's these two first columns, and then groups 13 through 18. Okay, so 1, 2, 13 through 18. So not the transition metals. Okay, we're going to leave those out for a minute. So we're going to talk about main group elements. One of the most important concepts to understand and remember is when naming and writing ionic compounds is this concept of charge. You have to be able to predict which ions are created from the elements on the periodic table between these main group elements. And they do follow a pattern for gaining and losing electrons. So use a periodic table to help you fill in your chart here. And I'll show you how to do that. So the first thing that we're going to do is look at potassium. Okay, potassium is right here. Let me pull this. I'm going to pull this over so it's half on and half off because we're just going to be talking about these elements first. So potassium, is it a metal or a non-metal? Well, it's a metal because it's on the left side of the periodic table. Okay, and is it going to gain or lose electrons? Well, we said before that metals tend to lose their electrons. So I'm going to put lose here. All right. So how many is it going to lose? Well, potassium is in group 1. That means it has 1 valence electron. So it's going to lose that valence electron. So when it loses 1 electron, it's going to create a positive 1 charge. Because remember, from 5.1, losing that electron, the electrons are negatively charged. It leaves the same number of protons in the nucleus. So there's only say, for example, potassium. It has 19 electrons and 19 protons. And when that 1 electron leaves, it still has 19 protons. But now it only has 18 electrons. So it has a proton left over that's not charged as it canceled out by the electron. So that creates a +1 charge. All right, so let's look at calcium. Calcium here is in group 2. Okay, so that means it is a metal. And it's going to lose electrons. And what charge is it going to have? Well, it has 2 valence electrons. It's going to lose those 2 valence electrons. So it's going to have a positive 2 charge. Because remember, it still has the same number of protons. All right. And so let's look at oxygen. Let's pull this down here now. All right, oxygen is a metal or a non-metal. Okay, we're going to say it's a non-metal because it's on this side of the stair step. Okay, and because it's a non-metal, it's going to gain electrons. How many? Well, it has 16. It wants to have 16. It has 6, so you always look at this last number. It has 6. It's in group 16, so it has 6 valence electrons, but it wants to have 8 valence electrons. So it's going to gain 2 valence electrons. All right, now electrons are negative, So when it gains 2 electrons, it's going to have a -2 charge. Okay, so you see how that works out? So fluorine, okay, fluorine now is right here. It's got 7 valence electrons. It's a nonmetal. So it's going to gain valence electrons. It's got 7. It wants 8, so it's going to gain 1. So it's going to have a -1 charge. Right? And phosphorus, right here. Phosphorus has 5 valence electrons. It's a nonmetal. So it's going to gain valence electrons. It's going to gain, so it'll have 8. So it's going to gain 3 electrons, which is going to give it a -3 charge. Right? Bromine. Let me erase this real quick so it doesn't throw us off. Bromine is on the right side of the periodic table. It's right here. Okay. It's got 7 valence electrons, but it wants 8. So it's going to, it's a nonmetal. Gain electrons. And since it has 7 and wants 8, it's going to gain 1 to be a -1 charge. All right. Aluminum. So continue to look at your periodic table. I'm going to move it over here so we can continue to write. Aluminum is a metal. It's just on the left side of that stair-step line. So it's going to lose electrons. Okay. And it has 3 valence electrons. Let me make sure. Yep, 3 valence electrons. So it's going to lose those 3. When it loses those 3, it's going to be a +3 charge. Okay? So we've looked and we've seen that no matter where it is on the periodic table, if it's in that group is going to do the exact same thing. So here, potassium is in group 1. It's got 1 valence electron. It's going to lose that to be a +1. Well, sodium is in the same group. It's going to do the exact same thing. It has 1 valence electron. It will lose that valence electron to be a +1. Lithium +1, rubidium +1, etc. So we have this pattern set up here. Oops, that's not what I wanted to do. We have this pattern set up here where these will all form a +1. These will form a +2. Skip this. These will form a +3, etc. across the periodic table. So if you look at the periodic table, it makes a stair step. So it looks like this when you're talking about charges. And this is written across the top of your periodic table as well. So if you look at the top, you'll see this. So if this is group 1, it's going to form a +1 ion. Group 2 will form a +2. Group 13 will form a +3. Group 14 that contains carbon usually does not form ions. So we're just going to say 0. And then it's going to step back down. The next group 14, -3, -2. 17 is -1. And then finally 18, those are the noble gases, so they don't even get involved in bonding anyway. So you have this pattern, +1, +2, +3, 0, -3, -2, -1. Okay, so if I pull this back up like this, and I know this is superimposed, but you know what? Let me bring this forward. Let me see if I can bring this to the front. Yeah, I can't bring it in front of the writing. Okay, so +1, +2, +3, 0, -3, -2, -1. noble gases. So you can remember that pattern: up 3, 0, 3, 2, 1, down 3, noble gases 0, then you'll get it right every time. All right, so let's take and do some practice on that. So here we have group 17. Group 17 are nonmetals. I'm just going to write non. Okay, they're going to gain electrons. I'm just going to write a G. So all of group 17 is going to have a -1 charge. Okay, group 2 are the metals. Okay, they're going to gain or lose electrons. How many? 2 electrons. So they'll have a +2 charge. Group 13, metals. So if they're metals, they're going to lose electrons, and they have 3 valence electrons, so they will be a +3. Group 1, metals, they're going to lose electrons. How many? 1. So they're going to be a +1 charge. Group 15 are nonmetals. That means that they're going to gain electrons. How many? Well, they're going to gain, so they have 8. They have 5 now. So they're going to gain 3 electrons. Okay, 3 electrons, those are negative, so it's a -3. Group 16, nonmetals. They're going to gain electrons up to 8. They have 6 now. So they're going to gain 2, -2 charge. Group 14, okay. Group 14, remember, that's carbon and silicon. So they're not going to do either. They're right there in the middle. They have 4 valence electrons, so it can't decide really if it's going to gain 4 or lose 4. So it doesn't do either. So, but they are considered to be nonmetals. So it's not going to do either, and it's not going to have a charge for this course. Now, when we get into AP chemistry, we're going to see that changes. If you decide to go the AP chemistry route. All right, so make sure you have that table filled out and you understand what's going on there. Transition metals. Now, transition metals we're going to talk about, start talking about more and more. Remember, the transition metals, there we go. Transition metals are the metals that are in this center area here, this pink section right here, transition metals. Now, we start talking about those in bonding because we have to, because they do get involved in bonding a lot. And so we don't have any set pattern where we could say this transition metal is this charge or this transition metal is this charge. I mean, there is a couple of patterns we're going to talk about, but not an overall pattern. So you're going to need to be told of the charge of that metal ion when you're using those transition metals or inner transition metals. There's another section here, this blue section here. These are called inner transition metals. Now, the reason they're called inner is because they're underneath the stair step. So again, the stair step goes like this. So they're underneath the stair step, but they're not in this transition metal block, the D block. They're called inner transition metals, and they behave just like the transition metals. Okay, so that's why they're called inner transition metals, because they're under the staircase, but they act like transition metals. So take copper, for example. Copper can either be a +1 charge or a +2 charge. Since it's a metal, it's going to have a positive charge, but there's no way to predict this just by its placement on the periodic table. So you're going to be told. So you're going to see it written like copper +1. That means it's a +1 charge, or copper +2. Now this is the symbol. You're going to see an Arabic number here representing the charge, +1 or +2. Normally, if it's +1, you won't see the 1. It'll just be a plus sign. Okay, but for the purposes of teaching, I'm going to go ahead and put in a 1 here. Now, if it's written in words, like it's not the symbol, but it's actually the word copper, it's going to have a Roman numeral. This Roman numeral here that's after the name is the charge. Okay, so this Roman numeral 1 means it's a +1 charge. This Roman numeral 2 means it's a +2 charge. Okay, so symbol, Arabic number, name, Roman numeral. Okay, and this concept applies to all the transition and intertransition metals, not just copper. Okay. Now, there is one small pattern that's on the periodic table that we use to remember zinc and silver. Zinc and silver never change. Their charge never changes, never varies like copper does. So we use aluminum as our anchor. Okay, and if we know that aluminum is a +3 charge, it never changes. Aluminum is +3. See how this steps down? It's a stair step. So if we step down from +3, this is a +2. And if we step down again, this is a +1. So zinc is always a +2. Silver is always a +1. I say always, it's not 100% of the time, but 99.9% of the time. There are, I think, 1 or 2 exceptions, but you'll be told those exceptions. All right, so again, use aluminum as an anchor. Aluminum is +3, so step down +2, step down +1. Okay, so that helps you remember that little pattern right there when you use silver and zinc. All right, so if you'll take out your reference materials, you're going to see on one of the pages over here these list of polyatomic ions. It's on the left-hand side of the page. Poly means many. Atomic refers to atoms. So many atoms that are bonded together that will form a charged ion. And these are not an exhaustive list. Like these aren't all that are ever used, but it's the most common ones. So you have a list here of the most common ones. So polyatomic ions bond in exactly the same way as, say, a monatomic ion, like sodium, mono meaning one atom, monatomic ion. Sodium bonds with chlorine, okay? And so these bond in exactly the same way. So instead of using chlorine or chloride as an ion, let's say that we use, let me get a simple one, hydroxide right here. Hydroxide is OH, and it's got a -1 charge. It bonds in exactly the same way. So since this is a charge of 1, and this +1, and this is a charge of -1, they come together and form what's called sodium hydroxide. Okay. Now I went over swap and drop in 5.1, and you do the same thing with these polyatomic ions. Okay, they act in exactly the same way. Except for when we start naming these, we don't change this name. So it's easier to name. Like, say, for example, we used this hydroxide just now. So this is going to be sodium bonding with hydroxide. So we don't change this name. You're going to see in a minute when I start telling you the rules of naming. If it's like chlorine, its name is going to change when it bonds. But on polyatomic ions, you don't change the name. All right, so just to review swap and drop, now that you know about charges and you're ready to start writing formulas for ionic compounds, the goal of forming ionic compounds is that it's a neutrally charged final product. In other words, if you have a +2 cation, like calcium, the anion over here either has to be a -2 or it needs to add up to -2 to cancel out this charge. Okay, so let's say, for example, sulfur. Sulfur here is a -2. So you can just put those two together because this +2 cancels out this -2. So the compound that forms CaS. But these numbers don't always match. So remember at 5.1, I talked about swap and drop, where you swap just the number, not the charge. So if calcium here is a +2, let's look at when it bonds to phosphorus, which phosphorus is a -3. So when we try to start balancing out these, it can get very difficult as far as, well, what number do they have in common, least common factor? And if the least common factor is this, how many of this? Okay, there's an easy way to do that. Remember, it's swap and drop. So if we take just this number and we swap and drop it to the subscript of this ion, and then we do the same. See, it's not pulling the charge over. Remember, it's just the number. Swap and drop that. Then we're going to get the correct formula for calcium and phosphorus bonding together. It's going to be Ca3P2. All right. So another thing to remember about writing these is that the cation always is written first. So it's always the plus ion and the negative ion. Okay, so the anion is written second. Okay, so remember, cation comes before anion. All right, so how do we name these? Well, it's really pretty simple. So for the first element, you're not going to do anything to it. You're just going to use the element name for the first element. For the second element, since it's an ion, you're going to take off its original ending. So here I've crossed through the ending of phosphorus, and you're going to add the ending "ide." So it's going to make calcium phosphide as the name of this compound. Okay. All right. So if we look at here, calcium plus chlorine, well, we have to know the ions in order to get the formula. So calcium is a +2 and chlorine's a -1. See here, the one's not written. Okay. So these don't cancel each other out and add up to 0. So we have to swap and drop. So this one is going to come down here as the subscript of calcium. This 2 is going to swap and drop down to the subscript of chlorine. So we're going to get Ca1. But remember, we don't write 1. So it's just CaCl2. So this 2 came over here and it's now the subscript. Now, if we're going to name this, the first one we don't change. So this is calcium. And since this is a single element, we're going to take chlorine. We're going to drop the ending "ine," and we're going to add "ide," IDE. So this is calcium chloride. Okay. All right. So let's do this example. So aluminum has a +3 charge. Okay. Oxygen is a -2 charge. So we're going to swap and drop because these don't add up to 0. So it's going to be Al2O3 is the correct formula. So to name this is going to be aluminum. Oxygen, take the ending off and add "ide," so it's oxide. Aluminum oxide. Okay. All right. Lithium and fluorine. Lithium is a +1 charge. It's in group 1 here. Fluorine is a -1 charge. Now this does add up to 0. +1, -1 adds up to 0. So we're just going to smash them together to form the compound. And the name of this is lithium fluoride. Okay, now remember, spelling fluoride is flu, just like the virus, fluoride, oride, fluoride. All right, magnesium. Magnesium is in group 2, so it has a +2 charge. Phosphorus, okay, so if you recall, let me pull over the periodic table. Phosphorus is over here in group 15, so that's going to be -1, -2, -3 using our pattern. Okay, so it's going to have a -3 charge. Okay, +2, -3 doesn't add up to 0, so we're going to swap and drop. So it's going to be Mg3 P2. Mg3P2 is the correct formula. So to name this, we're not going to change the name of the first one. So it's going to be magnesium. Okay, and this is phosphorus, so it's phosphide. So a question I get all the time is, how do you know it's not phosphoride since it's phosphorus, phosphoride? Well, you really don't. There's no set pattern on how many letters to drop. It's just once you hear it and you learn that phosphorus goes to phosphide, you just learn what it is. There's no set pattern on how many letters to drop. Like oxygen isn't oxygenide or oxygide. It's oxide. It's just something that you learn. All right, gallium. Gallium's not one that's used very often, so I'm going to go over here and locate it on the periodic table. I know it's a GA. Okay, it's in the same column as aluminum, so it's in group 13. Let me move it down a little bit more. It's in group 13. It's a metal, so it's going to make a +3 ion. Okay, so gallium is a +3. Bromine is one that's used a lot, so I know that's in group 17, so it's going to make a -1 ion. And you'll get to learn these just as quickly as I do. All right, so this doesn't cancel out and equal 1, so we have to swap and drop. So we're going to have a Ga1, but we're not going to write the 1, Br3. Okay, naming it, it's going to be gallium, bromine, bromide. So gallium bromide. Okay, zinc. Zinc is in that aluminum, zinc, silver pattern. So aluminum 3, zinc, +2. Sulfur. Okay, I know sulfur's a -2. All right, +2, -2 does cancel out, equals 0. So I'm just going to smash them together. And this is going to be called zinc. Here's another one. It's not sulfuride. It's sulfur, right? It's not sulfuride. You probably heard this name before. Sulfide. Sulfide. All right. Here's silver. Okay, so zinc's a +2. We know silver's a +1. Okay, bromine. Bromine's used all the time. Here it is again, -1. +1, -1 cancels each other out. So we have smash them together. No swap and drop needed. Silver. We're not going to change the name of the first one ever. Bromine becomes bromide. So see the pattern in naming these? It's really very simple. All right. So this is taking elements that are written, making the ions, the formulas, and then the name. So now we have a challenge, and this steps up the rigor just a little bit of seeing the name like this, taking it to ions, and then creating a formula. This is a little bit harder for students to grasp. All right, sodium. So we have sodium is a +1 ion, and we have chloride. We know chloride came from chlorine. So chlorine we know is a -1 ion. +1, -1. cancel each other out. So the formula unit is NaCl. Okay, same thing. Potassium is K. We look over here, it's in group 1, so it has a +1 charge. Okay, iodide came from iodine. Okay, iodine, symbol is I. If you don't know where that is on the periodic table, let's look real quick. It's in the same group as bromine here. Right there it is. Okay, so it has a -1 charge. Okay, +1, -1, cancel each other out. So it's Ki. Beryllium fluoride. Beryllium, you're going to learn, is Be. It's right here. So it's a +2 ion. Fluoride is in the same group as chlorine, bromine, iodine. Okay, fluorine is in group 17, so it's got a -1 charge. +2, -1, they don't cancel out. Okay, so we have to swap and drop. So we're going to have BeF2. This 2 is going to be swapped down to here. This 1 swaps down to here, but we don't write 1s, so BeF2. And for the last one, magnesium. Magnesium is Mg. It's in group 2, so we have a +2 ion. Nitride is nitrogen. Nitrogen is a -3 ion. +2, -3 don't equal 0, so we have to swap and drop. So we're going to get Mg3 N2. All right? Easy peasy. And you're going to see these words binary and ternary, especially binary. So I'll put this little guy up here to show you that bi is a prefix that means 2. So these are binary compounds, 2 elements bonded together. 1 element, 2 element, 1 element, 2 element. Binary. Ternary means anything more than 2. So there are cases where more than 2 elements bond together. Those are called ternary. Okay. And there's a different naming system for that. All right. But let's look at transition metals before we get to the ternary compounds. So transition metals, as mentioned earlier, they sometimes have more than one charge, or not at the same time, at different times. Like copper can either be a +1 sometimes or a +2 in other times. So everything we've learned up to this point is still going to apply with transition metals and making formulas with just one small change. Some distinction needs to be made in the naming to indicate whether we used a +1 ion, a +2, a +3, a +4. And this is done by placing a Roman numeral directly after the name. So think back earlier. Remember when I said, if you have the name written out like this, you're going to use or see Roman numerals to tell you the charge of this. So it's the same thing here. So if we have Roman numerals, that tells you the charge, and we have to include that Roman numeral in the name. So say, for example, if we take copper, and you're going to be told it's a +2, and we're going to combine that with chlorine, that's a -1, we're going to get copper chloride like this, because these don't cancel out to equal 1. So we have to swap and drop. The 1 comes over here for copper. This 2 is now the subscript of chlorine. Here's the formula. Okay, but we have to name that by showing that this was copper 2 that was used in this formula unit. So the way we write out the name is copper Roman numeral 2 chloride. So the name of this is copper 2 chloride, copper 2 chloride. Okay, so that's how we do it for transition metals. So you had to know the transition metals, or you had to be able to recognize them. And this applies also to the inner transition metals. Now remember, the inner transition metals that are underneath the stair step, okay, but they're not in the block of transition metals. All right, so here we have tin. Tin is a +4 ion, and oxygen. And it says here that oxygen, it doesn't have a charge, but oxygen really does have a charge. So it wants us to -2, recognize that charge and put it in there. So we're going to use a -2 here. Okay. So we have 10. Oh, this is just telling us the elements. See how it tells you the charge of all of these, but not these, because this is a set charge and these charges vary. So the ions is going to be Sn +4 and then O -2. Now we're going to see that these don't cancel out and equal 0, so we have to swap and drop. So the formula is Sn2O4. Now the way we name this, Sn is 10. Now remember, it's an intertransition metal, so we have to use a Roman numeral to show the charge. So 4, so that's IV, and then oxide. It takes the same rule where you change the ending to "ide." All right, so if you don't know Roman numerals, all you have to know is up to 4. Roman numeral for 1 is just an I. Roman numeral for 2 is just 2 I's. And you can either put them together like this, or you can write them separately. I've run them together. Okay. 3 is 3 lines like this. And then 4 is going to be IV. And sometimes I put a line, sometimes I don't, but you can do it either way. All right. All right. So here, PB is lead, F, fluorine. So it tells us here that PB, lead, is a +4. Fluorine's always a -1. So swap and drop, we're going to have PB 1, F 4. Okay, because these don't equal 1. Now the name of this, don't change the first element, lead. Second element gets changed, its ending is dropped, and we add "ide." So this is going to be fluoride. Remember, FLU, the flu. Fluoride got the flu. All right, PB2, Cl. This is lead 2 now instead of lead 4. Cl is always -1. So these don't equal 0. Swap and drop. So we're going to have PbCl2. This is going to be called lead. Chlorine, change the ending to "ide." Chloride. All right. Fe is iron. Okay, so it tells us this is iron 3. Oxygen, -2. See, it never changes. 3 and 2 don't cancel out to 0, so we're going to have to swap and drop. So this is going to be Fe2O3. Oh my goodness. You know what I've been forgetting to do? The Roman numeral. That's the whole point of this. All right. So we did 10. So lead is 4. So we have to squeeze in a 4 here. Okay. This lead is 2. So squeeze in a Roman numeral 2. I hope you caught that. All right. Iron. So this is iron. And what's the charge? 3. So we're going to do iron 3. Oxygen, oxide. Okay, I hope this didn't confuse you. Okay, mercury. Mercury is a transition metal. It's got a +1 ion here. So I'm just going to write the plus. Chlorine is -1. Okay, +1, -1 cancel each other out. So HgCl. Okay, mercury. We don't have to change the name of the first one ever. It's a +1 ion, so we're going to add a 1. And chlorine changes to chloride. All right. Chromium, Cr is chromium. Chromium here is a +2 ion combining with sulfur. Sulfur is a -2 ion. Okay, and I just want to make sure. Sulfur. Here we go. Right there's sulfur. So -1, -2. So it is a -2 ion. These do cancel each other out. +2 cancels -2. So just smash them together. Crs. Okay, so chromium 2 sulfide. There you go. All right. So now we need to go from name to formula, which again is just a little bit more difficult than going from formula to name. So here we have iron 2 oxide. So what are the ions? Iron. Now remember, this tells you the charge. So this is iron 2. Okay. Oxygen is always a -2. Okay. So we see here that these cancel out. So the formula is going to be FeO. All right. Nickel 3 fluoride. Nickel is Ni. It tells us the charge is +3. Fluoride is fluorine. Fluorine's a -1. These don't cancel out to equal 0, so we have to swap and drop. So it's Ni3F. Okay. Cobalt 2. The symbol for cobalt is CO. 2 means it's got a +2 charge. Nitride comes from nitrogen. Nitrogen's a -3 charge. Doesn't cancel out to 0, so swap and drop. So we have a CO3N2. Chromium. Chromium is Cr. Here it's a +3. Oxide is oxygen. That's -2. Oops, the 2 didn't come out. All right, so doesn't equal 0, so swap and drop. So we're going to get chromium 2, oxygen 3. Mercury 2 oxide. Mercury is Hg. 2 + 2. Oxide -2. This does cancel out. So we just smash them together. So this is HgO. Gold, you don't see that very often. Gold is one of those elements that does not bond very much. That's why we use it for so much jewelry, because it usually doesn't bond to other elements. So gold will stay looking nice on your finger. Whereas copper does bond readily with oxygen. So when you wear jewelry that's got copper in it, it'll turn your finger green because copper oxide is a green color. When copper bonds with other elements, it turns green. All right, so gold, the symbol for gold is Au. Okay, and it tells us here that this is gold 3, so that's a +3. Nitrogen is a -3. Okay, those do cancel out. So the symbol is AUN. Bismuth. Bismuth is another one that doesn't bond very often. You don't see that very often, but let me show you where it is on the periodic table. Bismuth is right here. Okay, it's at the bottom of this same group that nitrogen is in. Okay, so bismuth has a -3 because we know nitrogen has a -3. We just used it. It's in the same group, so it also has a -3 charge. Okay, so bismuth. Oh, I'm sorry. It's a transition metal, so it changes. Here it's 5. Oh gosh, V. I told you just needed 1 through 4, but I guess they're going to throw in a 5 here. Okay, so 5, remember the Roman numeral is just a V. All right. So this is +5. That's very, very unusual. Bromine, oops, is a -1. This doesn't equal 0, so we have to swap and drop. So we're going to get BiBr5 as a subscript. Okay, moving on. Ternary compounds. Remember, ternary, we just talked about that, 3 or more. So ternary compounds with a polyatomic ion. So if we go back to our polyatomic ion list that we saw here, remember I told you this is on your reference materials. These are groups of 2 or more elements that have combined together, bonded together, and it forms an ion. So if you'll see out here in the upper right quadrant of all of these, it tells you the ionic charge of these. Okay, so this you're always going to have available to you. I'll give you one of these anytime we take a test or a quiz. There's no need for you to memorize this list. No need whatsoever. Okay. All right. So writing compounds with polyatomic ions is not that much different than what we've already learned or talked about. The process is exactly the same. You have to look at the charges, and if the charges don't equal out to 0, then you still swap and drop. There's just one little added feature here, and I'm going to show you what it is and it will make sense when you look at this. So if we're going to bond magnesium here, that's a +2, with PO4, which is called the phosphate ion, we see it has a -3. Now let me go back to this list and show you. Okay, so PO4 right here, phosphate, PO4, it's got a -3 charge. So that's not something that you're going to have to memorize. You can look it up on this chart right here. Okay, so let's go back now. And we saw that that was a -3. So this +2 and this -3 don't cancel each other out. So we're going to have to swap and drop. So magnesium is going to get the 3 as a subscript. Do not change any of this. You cannot change this formula. It is a PO4. Think about that as a element. You cannot change anything about this. You can't change the P, you can't change the O, and you cannot change this 4. Okay, this is a unit. You cannot change that. So we have to write PO4. Okay, so we've swapped this 3 to here. We have to swap this 2 to here. So if we swap that 2, look, what does that look like? It looks like Mg3PO42. It looks like we need 42 oxygens. Well, that is absolutely not correct. So we need some kind of way that we can show that we need 2 of these. And the way we do that is by adding parentheses. Anytime you need more than one polyatomic ion, you're going to have to put it in parentheses before you put the subscript. Now we see we have 2 of these PO4 units. Okay, 2 of this whole unit thing. All right, and so that's the only change when you use polyatomic ions is you have to use parentheses. In the naming, nothing changed with either the cation or the anion. So we're not going to change the name of this. It's going to be magnesium. We never changed the name of the first one anyway, magnesium. And the good thing about this is we don't change the name of this either. If it's listed on that polyatomic ion chart as phosphate, that's what we're going to write, phosphate. Okay, so these are really harder to write because of the parentheses, but easier to name because we don't change anything. So this is magnesium phosphate. All right, and so in order to make this a little more clear, we have to have a flow chart so that we can see how we name ionic compounds. Now, going back again to this chart, ammonium right here Ammonium is the only polyatomic ion that we're going to use that is a positive cation. If you'll look, all of the rest of these are negative. Okay, so ammonium is the only one that's positive that we're going to use. So in this flow chart, you see here, does the compound contain ammonium? Well, all that's really asking is the first unit a polyatomic ion, ammonium? Okay, so on flow charts, yes always goes to the left and no always goes to the right. Okay, so if it is the anion, is the anion a polyatomic ion? So you're looking at the negative. Remember, anions are negative. So you're looking at the negative ion to see if it's a polyatomic ion. Okay, does the compound contain ammonium? So if you say no, is the cation a main group element? That means, is it from group 1, 2, 13, 14, 15, 16, 17, 18? Okay. All right. So let's just stick with, yes, it's a polyatomic ion. It is ammonium. So look at the anion. Is the anion a polyatomic ion? If it's yes, it's the ammonium plus the name of the polyatomic ion, like ammonium phosphate. If the answer is no, it's ammonium plus the element. You change, since it's the second element, change the ending to "ide." So if it was Cl, that's chlorine, so it would be chloride, ammonium chloride. Okay, so simple. All right, so is the compound ammonium? No. Is the cation a main group element? So is it in one of those 1, 2, 13, 14, 15, 16, 17? Yes. Is the anion a polyatomic ion? So is the second part a polyatomic ion? If it's yes, you're just going to name like magnesium and then the polyatomic ion name phosphate. If it's no, the metal plus the element changing the ending to "ide." So magnesium chloride. Okay, so go back up here. Is the cation a main group element? No. Is the anion a polyatomic ion? Okay, yes. So use the metal with the Roman numeral plus the polyatomic ion name. So say copper phosphate. No, use the metal with the Roman numeral and then the element changing to "ide." Okay, so there's a lot of things to remember here about ionic naming. Okay, so first, decide whether it's polyatomic ions that you're using. If it's not, remember, main group elements are separate than transition. Transition, you have to have a Roman numeral. Main group elements, you don't. Okay, so that's for the first. The second part of it, if it's either going to be a polyatomic ion or it's going to be a main group element. If it's a polyatomic ion, don't change the name. If it is not a polyatomic ion, then change the ending to "ide." Now, don't expect you to remember all these rules right off the bat here, and I know it can be confusing, so we're going to have lots and lots and lots of practice. Practice is really what solidifies all this information. Okay, one more thing I want to bring up. Unfortunately, spelling is going to count when you start naming these, because here's ammonium. Ammonium is bonded with chlorine. The ending is "ide," ammonium chloride. There's two polyatomic ions, ClO3 and ClO2. ClO3 is chlorate. ClO2 is chlorite. See, this is ATE. This is ITE. Okay. Some of them we have as OUS. They have endings as OUS. So I know I usually don't say spelling counts, but in this case, spelling does have to count. It has to count because whatever the ending is tells you what the formula is. Okay? So be very, very careful on the spellings of those. Ate and ite endings, when you see ate and ite or OUS, they indicate polyatomic ions being used. Okay, so if you see "ide," IDE, it's probably an element. Okay. If you see anything else besides ide, then it's probably look on that polyatomic ion list to see if you can find it. And of course, this is chemistry, so there's two exceptions: cyanide, which is Cn, -1 charge, and hydroxide, which is OH, -1 charge. Those are two exceptions. They end in ide, but they're polyatomic ions. Okay, I know, a lot to remember, but we'll get through it, I promise. All right, so that's a good place to stop. So if you're stopping and just doing this in parts, that's a good place to stop. You could have stopped before this, but this is definitely a good place to stop, because now we're going to talk about covalent. Everything we've talked up to this point is ionic. So now we're going to start talking about covalent, which is, believe me, it's easier. Okay? Much, much easier. All right. Covalent molecule naming. It's very simple compared to ionic. Like I just said, the molecule is made up of just two different nonmetals. The first step is to memorize 10 prefixes. So we have 1 through 10 here. The prefix that means 1 is mono. Di is 2. Tri is 3, like a tricycle has 3 wheels. Tetra is 4, like the game Tetris has 4 squares that are connected in different shapes. You could have 3 squares like this and then a square here, or it could be 4 in a row. Okay, tetra, or it could be 2 like this and then 2 up here. So the game Tetris is just 4 squares that come down and you have to put them in, you have to interlock them all to make solid rows. Okay, tetra means 4. Penta, 5, like the Pentagon. The Pentagon is a building in Washington that's shaped like this. Okay, Pentagon. Actually, it comes in a little bit like that. Anyway, it has 5 sides. Okay, penta. 6 is hexa. Okay, 7 is hepta. 8 is octa, like an octopus has 8 tentacles. Octa. Nona is 9, and deca is 10. So memorize these 10. 90% of covalent naming is done. Okay? Because the steps for naming these, you name the first element using prefixes. So all of these are going to use a prefix to tell how many elements there are. The only exception is if the first element has 1, so it's mono something, none of these start off with mono. Okay, so never, never, never start the name with mono. If it is just 1, you just drop the mono. The second step, always add a prefix to the second element that's in the compound. Always. There's no exceptions to that. All right, so let's look at this. Carbon, we have 1 carbon, so that's monocarbon. So we don't start anything off with mono, so we're going to drop the mono. So this is just going to be carbon. We have 2 oxygen. Prefix for 2 is di, so this is di. We're going to change, since it's the second element, we're going to change the ending to ide. So this is dioxide. And you knew that. You knew CO2 is carbon dioxide. Okay? All right. 2 nitrogen. So this is dinitrogen. Okay, so remember, on the first element, never change the name. Dinitrogen. 3 is tri. It's oxygen, so it's oxide. So this is trioxide. Dinitrogen trioxide. Okay. 1 sulfur, so it's monosulfur, but you never start off with mono, so we're going to drop that. So it's sulfur. 3 oxygen, trioxide. So see, this is a lot easier. All right, so boron, monoboron. We don't start with mono, so boron. 3 bromine, tribromine, bromide, tribromide. Okay. Silicon, there's 2 silicons, so this is disilicon. Remember, don't change the name of the first one. And this is 6 bromine, so it's hexabromide. Hexabromide. Okay. And 4 phosphorus, so it's 4 is tetra, so this is tetra phosphorus. 10 deca oxygen oxide, oxide. Okay, decoxide. Or you could say decaoxide. You could put the A in there, but usually I see it where it's the 2. If you have 2 vowels here between the prefix and the element, the one of those vowels is dropped. So it's decoxide. Okay. All right. So now we're going to go from name to formula. Very, very simple, because this tells you, these prefixes tell you exactly how many you need. So carbon, if it's just the name, there's just one of them. So that's carbon monoxide. You probably heard carbon monoxide poisoning. It's the poisoning that light comes out of the exhaust of a tailpipe of a car, carbon monoxide, mono 1 oxygen, so it's CO, carbon monoxide. Okay, chlorine, Cl, because there's just one, monofluoride, mono 1 fluorine. Carbon, C, there's just one, tetrafluoride, tetra is 4, so it's 4 fluorines. Remember, the number comes after the symbol, so it's 4 fluorides. Silicon dioxide, silicon dioxide is 2, so SO2. Dihydrogen, okay, so di 2 hydrogen, so it's H2. Monoxide, see, there's mono and oxygen, 2 vowels together. One is usually dropped to monoxide. So that's O, H2O. All right, so H2O is called, the official name of it, we call it water, right? The official name is dihydrogen monoxide. Dihydrogen monoxide. All right, dinitrogen. So that's N2, 2 nitrogen, pentoxide. So here, penta and oxide, 5 oxygen. So it's going to be O5. Okay, simple, simple. So the only thing that's going to throw you off now is, now that since this is so easy, anytime we see something, you're going to want to use prefixes for everything. Okay, because ionic naming and bonding is so difficult, you're going to want to use prefixes for everything. So you must resist that temptation. So when you're looking at something to name, the first question you want to ask yourself is this ionic or is this covalent? And how can you tell the difference? Metal, non-metal, 2 nonmetals. Okay, just like when we were drawing the Lewis structures, that's the first question you have to ask, because they're drawn differently. So naming, that's again the first question you have to ask. Is this ionic or covalent? If it's ionic, you're going to use that whole separate naming system. If it's covalent, we're going to use the prefix naming system. Okay, so resist that temptation to name everything with a prefix. All right, we finally made it to the end. We're going to talk about acids and bases, because naming of acids and bases are a little bit different. Actually, it's just the acids that are a little bit different. So here we're going to talk about the Arrhenius theory of acids and bases. And this is developed by Svante Arrhenius, a scientist. Bases are always going to have a polyatomic ion of OH. attached to it. So for example, NaOH is a base. Okay, so acids and bases. Okay, there's no difference in naming this because it's a base. So sodium hydroxide, sodium, and this is the polyatomic ion hydroxide, so this is sodium hydroxide. So bases are going to stay the same. There's not going to be any change. Acids, on the other hand, we're not so lucky with that. Acids are always, you're going to see this AQ after them. That means in the aqueous form, that means it's been dissolved in water. The compound has been dissolved in water. They will always begin with an H. So anytime you see something that begins with an H, it's an acid. There's only two exceptions. Hydrogen peroxide, which is H2O2. That's not an acid. And water, H2O, that's not an acid. Well, for now anyway. We are going to talk about water being an acid, but for naming, no, it's not. Okay? And I'll let you know when that comes up. So remember, binary. Bi means two. So binary acids are only made up of two elements. Since the first element's always hydrogen, the second element's going to be a nonmetal anion. For example, hydrogen plus chlorine, hydrogen plus bromine, hydrogen plus iodine, hydrogen plus fluorine, hydrogen plus sulfur. See, all of these second anions are elements from the periodic table. Okay? And so when you see a binary acid, hydrogen plus one other element, you're going to use the naming system where it's hydro and then a stem here. So it's the stem comes from whatever element it's bonded with. So this is chlorine. Well, here it uses fluorine as the example. So for here, hydro, because it's hydrogen plus an element, and then fluorine, but we're going to change the ending. So remember, fluorine is Fluorine. So if it's an acid, take off this ending and add ic. So this is hydrofluoric, and then the word acid. Hydrofluoric acid is HF. All right, so if we're using that same pattern, okay, so here we see two elements. It begins with an H, so it's an acid. So this is going to be hydrochlorine. We're going to change the ending to ic, hydrochloric acid. Okay, so hydrogen and bromine, it's going to be hydrobromine, bromic acid, hydrobromic acid. Okay, HI, hydro, iodine, iodic acid, hydroiodic acid. And then hydrogen and sulfur, sulfur becomes sulfuric, hydrosulfuric acid. Okay, so this is just for binary acids, hydrogen plus some element. Okay, but they also bond with polyatomic ions. So these are called ternary acids because ternary, three or more, 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, 1, 2, 3, 3 or more. So when it's a ternary acid, it's hydrogen bonded to a polyatomic ion. Okay, and the name comes from the polyatomic ion name. Okay, so the name of the acid is based on the polyatomic ion name. So SO4, so let's go down here and look for SO4. It's right here. So sulfate. So this is the sulfate ion. So the name of this acid is sulfuric acid. Okay, now if you'll look here, we see an sulfurous acid. So how can you tell the difference between sulfuric and sulfurous acid? So spelling does count, and the sound of the name counts. So sulfurous, we see uses SO3. So this is SO3 here, sulfite. So sulfate was used to the first one. Sulfite was used on the second one. Okay. So how do we figure out the name? Well, I have a little rhyme here, or a little saying. And you see this guy is, oh, so sick. He has a sad tummy. So if you remember this sentence, I ate an acid and now I feel icky. Last night, it's a misspelling of the word night. All night, I felt nauseous. Okay. So what this means is if the polyatomic ion ends in ate, you're going to change the ending to ic. So see here we have sulfate. Sulfate goes to sulfuric, ic ending. Okay. All night, ITE, if the polyatomic ion ends in ite, you're going to change the ending to us. So on the second one, we use sulfite. Okay. So sulfite, ite, is sulfurous acid. Okay. All right. So let's go back. Two elements, hydrogen plus another element, hydro something ic acid, polyatomic ion, you're not going to use hydro. It's going to be based off the name, and you're going to change the ending, whether the ending was ate or ite. Okay, so this is sulfuric acid. Okay, sulfurous acid. All right, so NO2. Let's find NO2. It's right here. It's nitrite. Ite goes to us, so this is nitrous acid. NO3, here we see is nitrate. Ate goes to ic, nitric acid. So nitrous acid, nitric acid. Okay. Here, hydrogen is bonded to chlorine and oxygen, so ClO3 must be a polyatomic ion. Let's find ClO3. Where is it? Right there it is, ClO3, chlorate, chloric acid. This one, hydrogen, ClO2. So ClO2 is right here. This is chlorite, so this must be chlorous acid, chlorous acid. All right. So arsenious acid. So this ending is us. So that must be arsenite because us came from ite. So it's arsenite. So let's find arsenite right there. Arsenite, not arsenate, but arsenite. So this is ASO3, negative 3. ASO3, negative 3, right? So this tells you how many hydrogens you need. Because remember, swap and drop, hydrogen's always positive. Okay, so if we swap and drop, we're going to need one of these, but we need 3 hydrogen to complete. So this is going to be H3ASO3, arsenous acid. All right, acetic. Ic comes from ate, so this is acetate. Acetate, right there it is, acetate. C2H5O2, negative 1. So we only need 1 hydrogen because that's negative 1, so it's H. We're going to put the hydrogen in the front, and then we're going to write this acetate ion, C2H5O2. Acetic acid. Acetic acid is the chemical name for vinegar. Vinegar is acetic acid. So that's the formula for vinegar. Pyrophosphoric. So this is pyrophosphate. Pyrophosphate. So let's go down here. Pyrophosphate. So that's P2O7. And it has a negative 4 charge. So it's going to need 4 hydrogen. So it's going to be H4. And then write this, P2O7. Okay, pyrophosphoric acid. Thiocyanate acid, it come from 8, so this is thiocyanate. So let's find thiocyanate right there. Thiocyanate, SCN -1. So since it's -1, that means it just needs one hydrogen. So SCN. So that's weird. It has 4 capital letters. Thiocyanic acid. Thiosulfuric, ic comes from 8. So this is thiosulfate. So here's thiosulfate right here. It's S2O3 -2. So it's going to take 2 hydrogens and then S2O3. Okay. Periodic acid, periodiodate, right there it is. Periodate is IO4 -1, so it just needs 1 hydrogen, and then IO4, periodic acid. All right. I know this is a lot. I'm sorry, but we're going to do a lot of practice and we're going to spend a long time on this. Okay. So types of acids. Last thing here, acids with 1 hydrogen are called monoprotic because mono means 1. Protic comes from the word proton because hydrogen, remember, has just 1 electron. And so to become an ion, it loses that electron. So the hydrogen ion is just really that 1 proton because hydrogen has 1 proton, 1 electron. So if it loses that electron, all that's left is a proton. So sometimes the hydrogen ion is called a proton. Monoprotic acids mean you just have 1 hydrogen in the acid. So nitrous acid is a monoprotic acid. Acids with 2 hydrogens are called diprotic. So let's find one with 2 right here, 2 hydrogens. So the prefix for 2 is di. So sulfurous acid is diprotic acid. And then any acids with 3 or more are called polyprotic. So here's monoprotic, diprotic, and polyprotic. Poly means many. So polyprotic, more than 2. So 3 or more polyprotic acids. So pyrophosphoric acid is a polyprotic acid. Arsenious acid is a polyprotic acid. You're going to see those words used, and it's going to expect you to know what those mean. Okay? All right. And that is it. Whew, this is a long one. And I do apologize, but remember, you can or you should have done this in chunks, 2 to 3 chunks. So make sure you slap that like button right across the face. Give me a thumbs up and a subscribe.